So today another power supply repair. This is a switching power supply from a lithium-ion charger or a battery charger. And it wasn't a small charger. This power supply is probably a couple hundred watts. It was given just this power supply, not the entire charger. But this is basically a power supply with minus voltage going in here and 12 volts coming out here. Or a voltage in this ballpark. The output was soldered here and some fan connector and another connector, not sure what it is. And an NTC thermistor for overheat protection. Here's the connector for the minus voltage going in, the fuse, some metal oxide varistor in parallel for overvoltage protection, some series NTC thermistor for inrush current limitation, then some Y capacitors for interference suppression, an X capacitor, the first common mode interference suppression inductor, another pair of Y capacitors, another inductor here, capacitor, X capacitor, the bridge rectifier, a small polypropylene capacitor in parallel to the output, the DC voltage. It doesn't go straight into the smoothing capacitor because there is this active power factor correction circuit, the active power factor correction inductor, the switching transistor and the diode. It's the typical boost power factor correction. Then there is this smoothing capacitor, 450 volts, 220 microfarads. And after this power factor correction circuit, it goes into the actual power supply, which is probably a half bridge, 2 transistors, the main transformer, the DC decoupling capacitor in series with the primary. I guess this is the gate driving transformer for these transistors. They're N-channel MOSFETs. And this thing is, I was thinking it's a current sensing transformer. The primary of this one is in series with the primary of this one, the main transformer. But it has way too many turns for a current sensing transformer. So I guess it could be actually a resonant inductor, which happens to have some auxiliary winding here on it. The main winding is here. Another reason I think it's resonant is because there is no secondary inductor here. The secondary of this transformer goes into this pair of rectifying diodes, which actually might be synchronous rectifier transistors instead, and then it goes straight into these output capacitors, electrolytic ones, without any inductor. And having no inductor here to average the voltage coming from the secondary, I guess it's not a pulse width modulation but a frequency modulation, moving it closer to resonance or farther from resonance. And yes, these are MOSFETs in a synchronous rectifier, these are not diodes. These actually rectify the voltage more efficiently, with less voltage drop and less losses than diodes. First, let's do some tests and measurements without applying power. I will show how to test the components in it and potentially find the bad one. And of course, before doing anything, it's better to check the primary capacitor for a charge. And then the measurements. Using a continuity test, you can test the fuse. It's not blown. The interference suppression filters. Not open a circuit. A diode test can test the bridge rectifier. A half a volt from one AC terminal to the positive and from the other AC terminal to positive. And also half a volt from the negative to one AC terminal and from the negative to the other AC terminal. A good bridge rectifier. Also the NTC thermistor is just a couple ohms, so it's not open. It's good. Now the MOSFET in the power factor correction. From drain to source, some capacitor charged and it's not shorted. Source to drain, we can see the internal diode in it. Measuring gate to source. This is probably the voltage drop of some gate driving circuitry. It's not a dead short gate to source, so it's good. The power factor correction diode should be half a volt in one direction and it is, so it's good. You can see some other diodes here, so why not check them? This is probably a Schottky or lower voltage drop. Another diode here. Again a good diode in forward. 2 small diodes. This one, it's not a Schottky, it has a higher voltage drop. And this one could be a Zener, but you can test it for a short or open circuit by measuring it in forward like a normal diode. Some small bipolar transistor probably here. Base to collector, base to emitter, nice. And even a smaller transistor, collector to base, emitter to base, PNP now. This diode would look suspicious, but it actually has a 22 ohm resistor in parallel, so it's fine. This one is the same case. This is the gate driving transformer. From the secondaries of it, it goes into the gates of the half-bridge transistors. I guess it's charging the gates via 22 ohm resistors and discharging them straight through the diodes. Of course, the half-bridge MOSFETs. No short drain to source here. No short drain to source here. Source to drain. The half a volt voltage drop, typical, good. The gate to source is going to be actually going through these resistors and the secondaries here in the gate driving transformer. It's not a short in the transistor. And these packages look like transistors, but they're actually double diodes, 2 in a series in one package. This is good. This one diode in it, and the other diode, good. Of course, these 3-pin packages are confusing. It can be actually a transistor, but then it says Q. It can be a double diode, it says D, or it can be a chip in a 3-pin package, and then it says U on it. So based on these letters, you can tell if it's a chip in a 3-pin package, a transistor, or a double diode. Even more transistors here, an NPN bipolar transistor base to collector, base to emitter. But it's also better to check it between the collector and emitter, because if you're only checking base to collector and base to emitter, you could actually miss a short between the collector and emitter. So I'm checking actually collector to emitter now, and it's not shorted. There is some voltage drop of something else in the circuit, I guess, or maybe some internal anti-parallel diode. The important thing is it's not a short. Another NPN base to collector, base to emitter, no collector to emitter, no short. This is good. Some diode. I'm not even going to test all of them on a camera. There is a ton of them, and about 8 more tiny transistors. I tested all 8 of these transistors here. These seem good. I guess there is nothing wrong on this side of the board. The SMD components seem good. Of course, except the chips, which you can't easily test using a multimeter. I should also check the synchronous rectifier MOSFETs here. It actually beeps but momentarily as it charges a capacitor in the circuit, and then it's not shorted. Another MOSFET, not shorted, drain to source, or source to drain. It again charges the capacitor and shows a voltage drop of a diode in it, not shorted. The gates are not shorted to the sources, the other one as well. This is the voltage drop of some circuitry driving the gate, not the gate itself. There are some ceramic capacitors. You can also check these for shorts, no short. Even more ceramic capacitors, some voltage drops of something else in the circuit, not the capacitors themselves. Of course, also the electrolytic capacitors can be tested for shorts, even though it's more common for electrolytic capacitors to fail open circuit or high ESR or low capacitance. And these big 2 capacitors, both in parallel, it beeps because they charge and no short. The voltage goes up on them, the primary one. And of course, you have to be sure it's discharged before testing it. It's not shorted. There is a couple more electrolytic capacitors, small ones on the primary side, not shorted, not shorted. Film capacitors, these brown or red ones, no short. Was this a short or is there something charging? Yes, there's a capacitor charging actually. This might be confusing, it momentarily beeps like a short circuit, but it's not. This capacitor in a series with the primary, not shorted. Some tiny ceramic capacitors parallel to the transistors. Now of course the ESR of the electrolytic capacitors, and this one is working again. I should make a video about what was wrong with this one. Let's measure the secondary big electrolytic capacitors. The 2 secondary capacitors in parallel show a couple milliohms in a negative sometimes, because now it's overcompensated for the resistance of the leads, I guess. But these capacitors are good. The main primary smoothing capacitor, less than 100 milliohms. This should be good. There are some small 100 micro capacitors, 2 of them on the secondary side. This is reading about 60 milliohms, good. Again about 60 milliohms, nice. Some small 47 micro capacitors, 200 milliohms, good for low capacitances. Another 47 micro, 300 milliohms, good for a small capacitor. That was these capacitors here. There is this very low resistance power resistor current sensing shunt. Let's measure this one. It's such low resistance the multimeter can't really measure it properly. 0.15 ohms. Oddly enough, this battery internal resistance tester can actually measure very low resistances. And the resistor is very close to the nominal 150 milliohms or 0.15 ohms. Nice. The odd thing is this resistor was actually soldered. Somebody replaced it. Did he actually put the right value in it? And typically when this resistor fails, there might be some other problem. For example, the transistor with shorts destroys the resistor, but the transistor here is good in the power factor correction, and the transistor doesn't seem to be soldered, it's original. The resistor is brown, green, silver, gold. I tested almost everything and I still can't see anything obviously wrong here. I could measure all the tiny SMD resistors in it, but at this point it might be faster to find the problem by plugging it in and measuring it with power in it. And of course for demonstration I'm testing almost all components in it, but typically you start with the most unreliable ones, or the power components that fail most often. Typically you're testing the ESR of electrolytic capacitors first. This is by far one of the most common failures. You're testing the fuse to see if something shorted in it, maybe the NTC thermistor for open circuit, the transistors, the diode, the bridge rectifier, maybe the current sensing shunt, which if it's blown open, there tends to be a short circuit in the transistor where it's sensing the current. But I don't see any obvious problem, so at this point I should probably power it, but before this, let's actually try to ring test some of the transformers. This is to verify there are no short turns in the transformers, and this one shows a lot of rings, so it's not bad. I can also ring test the power factor correction inductor, also quite a lot of rings, not a bad inductor, no short turns in it. The resonant inductor, I guess. This is a lot of rings, no short turns. Maybe the gate driving transformer should be also ring tested. This is still showing enough rings. It looks like no short turns. This was the primary. Here are the secondaries, one, the other, no short turns. Even though sometimes this one is skewed by the circuitry connected to it, so a low number of rings doesn't have to necessarily mean short turns. And the power transformer, you're typically ring testing just the primary. And I should also mention, typically you can measure the ESR of electrolytic capacitors in a circuit, but you can't measure their capacitance in a circuit. But this doesn't matter, because a high ESR is a better indicator of a bad electrolytic capacitor anyway. But now of course everybody's screaming power it, so let's power it. But of course for case something shorts, I'm putting a lamp in a series. And let's plug it in. It blinks. It's actually blinking. Because for this power of a power supply, this 100 watt lamp is a too low power, too much resistance in series, but it finally managed to charge this capacitor, it seems. Let's flip the board. I'm definitely showing a good example here, touching a live mains board here, but anyway. Let's measure the voltage on the main smoothing capacitor after the power factor correction, and it's showing about 390 volts, which is more than the rectified mains. 230 volts times the square root of 2 would be about 325. So the power factor correction is working and it's boosting the voltage. But the output, absolutely no voltage. And this means the problem is probably in the power supply section, not in the power factor correction section. Let's give it a bigger lamp, 200 watts, and let's see. No, the start is better without the blinking. This one was too much resistance in a series. Two 10 watt lamps in a series, trying to load the power factor correction, and it works under load. I can hear a little bit of buzzing, and I can smell something very hot. I should look at it using a thermal camera. This lamp is a bit hot. Some diode, I guess, or transistor hot here. One transistor is bloody hot here. It's supposed to be on a heat sink. And control chip on the secondary side is hot. And one small component here. So let's use macro lens. This is some resistor on the primary side is hot, but not super hot. This transistor is quite hot with no heatsink, but it's odd because in the half bridge, just one is hot and the other one is not. And on the secondary side, the control chip is hot and one transistor here is hot. Flipping a live board here, and this is hot here. This is the transistor in the half bridge. This is under the chip and the transistor on the secondary side getting hot. No through hole component other than this transistor is hot actually here. What the hell? Now I looked at it and the LED on the secondary side is LED. And there is 15 volts. I guess it's the nominal voltage. I was thinking 12, but it can be 15. And these capacitors are rated 25 volts, not just 16, which would be typical for 12 volts. But let's unplug it and let's take a look at the transformer. I noticed it actually says 15, 300 watts. Is it 15 volts, 300 watts? That would make sense. It's nice when it magically fixes itself for you. Plugging it in once more, and it starts up. You should of course try to load it, but without the heat sink it's tricky. It's not easy to fix something when you have just a piece of the machine and not the whole machine. Just very briefly try this. It shuts down. Let's try a 10 ohm resistor, which should draw 1.5 amps from 15 volts. If the power supply is 300 watts, it should be able to supply 20 amps. It started up again, loading it with this resistor. It does not shut down under this load. One transistor is cold, The other one is getting hot. That's weird. In a half bridge the transistors should be equal, and they shouldn't really be getting very hot with no load or very little load. This is just 7% of the full load. The imbalance in the temperature of the transistors is very suspicious, so it's oscilloscope time. Let's measure the waveform on the transformer primary, the main transformer. Let's plug it in, and here's the waveform, which is not exactly symmetrical. The rising edge is completely different than the falling one. How does it change with the 10 ohm load? Again, not symmetrical. Is one of the transistors bad, or is the gate driving signal wrong? Let's measure the primary of the gate driving transformer now. That's odd, it's getting a signal in just 1.5 cycle. And again, trying it with the load. Not much difference. The gate of the hot transistor is getting this. There's no wonder it's so hot. It's like 75% duty cycle, but a too low voltage for it to turn completely on. The duty cycle should never be more than about 50%. And the other transistor, the one that's not hot, is getting this. Now it seems simple. The signal going into the gate driving transformer primary is completely wrong. It seems the primary is switched by some bridge of transistors here. It's meant to be switching in both polarities, but it's switching just one polarity, just 1/2 cycle. I guess I missed a bad transistor in here, or the signal going into the transistors is wrong. Did I actually test these transistors? If I did, it wasn't on camera, which I sort of regret. This is base to collector, nice. Base to emitter, nice NPN transistor. The other one is the same type. Hell no! This is shorted, base to collector, base to emitter, all shorted. Emitter to collector, shorted. The lower ones are PNP, collector to base good. Emitter to base good. No short between emitter and collector. The upper one NPN also. But this PNP, collector to base, actually seems good or slightly lower than it should be. Emitter to base appears shorter, but it might be because the emitter and base of this one is connected to the emitter and base of the upper one. So let's desolder the upper left transistor. They didn't even destroy the board, nice. Out of the circuit, still shorted. Now the PNP transistor under it, collector to base good, emitter to base still shorted. So it wasn't just this one, still shorted emitter to base out of the circuit. A simplified schematic here. From the secondary side control chip it goes into this bridge of small NPN and PNP transistors. They amplify the current, and via a capacitor it goes into the primary of the gate driving transformer. And this one isolates it from the primary side. And on the primary side that's the half bridge of the MOSFETs, which via the capacitor and the inductor goes into the primary of the main transformer. And the gates of these transistors are driven using the secondaries of the gate driving transformer and couple components. Of course these two secondaries go the other way, so when one transistor is on the other one is off. And these two transistors are the bad ones. This one is shorted all the way, this one base to emitter. So this side of the GDT primary is basically still positive, connected through here. The other side is still getting the signal, 1/2 of the driving signal here. And this is what we can see going to the gates. It actually should be something like this. I put 2 new transistors on it using this, if you can imagine it. And a bucket of rosin and this. The excess rosin can be cleaned using ethanol if you want. But you can leave the rosin on it, it's not conductive. And that's it after cleaning it, you wouldn't even tell it was changed. Oh crap, then the other NPN transistor in the bridge also failed here. I also had to change it. But anyway, now let's test it with these 3 transistors changed. The only one original in this bridge is this one. I guess the NPN transistors are crappy. This PNP failed just because this one was shorted, not on its own. Now of course the scary part. Then the LED is lighting up, nice. Now again measuring the primary of the gate driving transformer. Not much duty cycle, this is not loaded. When I load it, this is actually how it's supposed to look like. Nice symmetrical waveform. Nice. And the transistors are both cool. And this is a brilliant idea, isn't it? But I'm not grounded. And the transformer primary, no load, loaded. The power factor transistor is cool, the diode cool. These are both warm and equal. These are also a bit warm and again equally, so it seems to be working right. And it's weird how initially it wasn't starting at all, but I guess maybe this transistor was also completely shorted, but then the current blew the collector open in this one, so it was no longer shorting the supply rail on the secondary side. Now it's lighting up a car headlight lamp, but just briefly, and this one lights up because it's too much current. This one in series with the mains would have to be a much higher power for this. And of course some example schematic in the datasheet of the secondary side control chip. Here's the chip with some small components around it, the voltage sensing, the bridge of small transistors driving the gate driving transformer, where I changed 3 transistors, and 2 half bridges of transistors driving the gates of the synchronous rectifier MOSFETs. And here's the power section example schematic, the MOSFET half bridge, some components for the gates, the tiny ceramic capacitors parallel to them as snubbers, the resonant inductor capacitor, the primary of the main transformer. This one shows some current sensing transformer which is not there. Maybe it's using the auxiliary winding on this resonant inductor for that purpose. And the example schematic shows 2 output voltages, but in our case it's just 1 voltage, so it's like this. And there is no inductor and a second set of output capacitors reducing the ripple, so it's like this basically. And that's about how the power section of it actually is. Of course the control chip is on the secondary side, so it has to initially get its supply voltage from something else, then its output. So initially it's getting its power from this auxiliary power supply, which is basically a voltage doubler with 2 diodes and 2 capacitors connected to the auxiliary winding of the power factor correction. And why it's a doubler? Because the peak voltage in either polarity can vary, but the sum remains about constant. Or the voltage swing or peak to peak level remains constant, because it's a boost converter with a constant output voltage basically. But now of course the scariest part, testing it without the lamp in series. Let's just plug it in and see. No explosion now. Of course I have to test it only briefly because it has no heatsink. And it's working. 2 lamps. 1. Both. That's about 12 amps. That's about as far as I'm willing to go without the heatsink. I was thinking about making some makeshift heatsink for it, but it's probably better if I return it and it will be further tested in its original place. The gate driving transformer gets a nice symmetrical signal. And the gate of one of the synchronous rectifier MOSFETs and the other synchronous rectifier MOSFET gate. And if anybody's interested in the marking of the power component is here, and of course the video is getting bloody long. These two should be equal, and the synchronous rectifiers. Just for case, is there any damage done to the transistor that was super hot? It's an N-channel MOSFET, 3.9 volts gate threshold voltage, 3.03 nanofarads gate capacitance, the on-state resistance 0.4 ohms, and the forward voltage drop of the internal diode 559 millivolts. And that's the other one which wasn't hot, and the differences are negligible. Using a better internal resistance meter to measure the on-state resistance of the MOSFET. This one is totally meant for this purpose, but it seems to work. 265 milliohms. The datasheet says 330 maximum, and the one that was super hot, 263 milliohms. It's super similar to the other one, so I assume it's not damaged. And this thing seems to measure the on-state resistance of a MOSFET much better than this, more accurately. This is for batteries, but I'm using it for electrolytic capacitors to check the ESR. Now for MOSFETs, for the on-state resistance, it seems to have many uses. The Kelvin connection probes are really useful, even for very low resistance resistors which a multimeter can't measure. That's the power factor correction chip. And the 8-pin chip on the secondary side is just an op-amp. And I've even cleaned this. So that's it, the power supply is repaired. And if you like my videos, please consider subscribing, with the notifications on of course. And you can also support my channel using Patreon or using the thanks button, based on how much you learned from my videos. And a big thanks to all of you who already support me. This channel couldn't be possible without you.